Hello everyone. In this presentation, I will introduce how to describe fluid motion in fluid mechanics. The main idea is that fluid motion is not just about where fluid is going, but also about how small fluid elements translate, rotate, change shapes, and change volume. Let's begin with the velocity field. In fluid mechanics, the velocities of a fluid at a point is represented by a vector field that depends on space and time. In other words, the fluid velocity can vary with x, y, z, and time t. If we know the velocities at every point in the flow field, then we have the complete description of the flow. This is powerful because it lets us analyze how fluid moves around objects, such as airflow over a swing or water through a pipe. So the velocity field is foundations of describing fluid motion in a precise mathematical way. A general motion of a fluid element can be described as the combinations of four components. These are translations, volumetric deformation, angular deformation, and rotations. Translations means the fluid element moves from one location to another. Rotations means the entire element spins. Angular deformations means it changes shape, especially when right angles between lines inside the element change. Volumetric deformations means the element changes size. In practice, fluid motion is often a superposition of all four effects happening at the same time. These slides give us a conceptual framework for the rest of the presentations. Now let's focus on rotational motion. Rotational motion is described by the angular velocities, usually written as omega. To visualize this, imagine a tiny rectangular fluid element in the xy plane. As the surrounding flows acts on it, the element may begin to rotate. The rotation is related to how the velocity components change with positions. By examining the rate of angular deformation along the sides of the element, we can determine the average angular velocities about an axis, such as z-axis. So rotational motions help us quantify the spinning behavior of a fluid element rather than just its translation through space. This slide extends rotational motion into vector form. The angular velocities components can be written in terms of velocity gradients, and from vector calculus, we know that try the angular velocities is equal to the curve of the del operators in velocity vector field, which is called vorticities or zeta vector. Vorticities measure the local spinning tendencies of the flow. If the curve of the velocity vector field is zero, then the flow has no local rotation and is called irrotational. That does not necessarily mean the fluid particles are not moving quickly. It simply means they are not spinning locally. This distinction is very important in theoretical and applied fluid mechanics. Here we apply the vorticity concept to a two-dimensional flow field. The question is whether the given flow is irrotational. To answer that, we evaluate the rotation vector using the velocity components and the expression for angular velocities. If the relevant component is zero, then the flow is irrotational. The example shows exactly how we move from the velocities field to a physical conclusion about rotation. This is a good reminder that fluid mechanics often connects mathematical derivatives directly to physical meanings. So the example is not just a calculation. It is an interpretation of the flow behavior. Next, we introduce the stream functions, usually denoted by size functions. For a steady, incompressible two-dimensional flow, where the velocities have only two components, u and v, the stream functions provide a very useful alternative description of the flow. It is defined so that its derivative gives the velocity component and lines of constant size are called streamlines. That means the stream functions allows us to visualize the flow pattern directly. This is especially helpful because, for incompressible flow, the continuity equation is automatically satisfied when velocity components are defined in terms of a stream functions. This makes it a convenient tool for flow analysis. This example shows how to determine the stream functions from a known velocity field. We are given the two velocity components in a steady, incompressible, two-dimensional flow. From the definitions relating u and v to the stream function, we integrate to find the size functions. Once the size functions is known, we can sketch streamlines by setting size equal to constant value. These streamlines help us to see the flow pattern and directions visually. So this symbol connects the mathematical procedures of integrations to a graphical interpretation of fluid motion, which is one of the reasons the stream function is such a useful concept in fluid mechanics. Now let's discuss angular deformation, which is also called shearing deformation. This occurs when a fluid element changes shape so that lines inside the elements are no longer perpendicular or parallel in the same way as before. In other words, the shape distorts even if the volume does not necessarily change. The rate at which the right angle changes is called the rate of shearing strain. Mathematically, this depends on combinations of velocity gradients. Physically, angular deformations have described how fluid element is being sheared by the surrounding flow, which is closely related to viscous effects and internal frictions in real flows. Finally, we have volumetric deformations. This refers to a change in the size or volume of a fluid element without necessarily changing its shape. If the fluid element expands or contracts, we describe that behavior through the volumetric rate of deformations. Mathematically, this is related to the divergence of the velocity field, or del.v. If the divergence is zero, the flow is compressible, meaning the fluid element volume does not change as it moves. If the divergence is non-zero, the element is either expanding or compressing. This concept is essential for understanding compressible versus incompressible flow behavior.